Hello everyone, this is lecture 9 of course PE 645. In today's lecture we are going to revisit the artificial intelligence workflow in Radiomics that consisted of different steps from data acquisition to classification and performance evaluation. But in this lecture we are going to deal with 3D datasets. We have dealt earlier with 2D datasets that consisted of images, and we extracted the features from these images and applied them to a classifier and then reported the performance that was on the long dataset, where the long dataset consisted of two regions, left and right, and we have merged between them horizontally some features for the left lung and others for the right lung. So now we will acquire a 3D dataset and apply the same process onto these datasets from data acquisition, feature extraction, classification, and performance evaluation. So let's begin. The dataset that we are going to deal with is called MED or Medical MNIST. It consists of 2D and 3D biomedical image datasets that can be used in image classification, and they provided it publicly that can be downloaded and utilized in your project. As you see here, they provided a preview on different datasets that exist in this database. Some of them are related to 2D and others are related to 3D. And in this lecture, we are going to deal with two datasets in the 3D version. We are going to deal with organ MNIST and nodule MNIST. So to acquire the dataset and download it, in the link provided in this lecture, you can scroll down and stop by the name that refers to nodule MNIST and organ MNIST in the 3D version and download them. You will find the download link for each dataset. The second step is to extract the features from each dataset individually. For the nodule MNIST 3D dataset, they mentioned that this dataset is derived from the LIDC dataset, which is a comprehensive collection of lung nodule images from the thoracic CT scans, and this dataset is binary, where they merged and grouped malignancy levels 1 and 2 into negative class and levels 4 and 5 into the positive class. They also divided the dataset and provided the split already, and the ratio between training, validation, and test is 7:1:2. So when we proceed to extract the features from the dataset in this lecture, we need to extract the features for the training and the feature for the testing, because the classifier will require a dataset or some features for training, and after training we need to evaluate the generalization of the trained model using the testing subset. We need to extract different features from each dataset, which are first order features GLCM, GLRLM, and GLSZM, and finally the shape features. And during the extraction, as mentioned, we need to add the class as the last column to be used in the classification process. For the second dataset, it's a multi-class classification dataset. It consists of 11 different body organs, which consists of 115 CT scans for training and 16 CT scans for validation. They also provided the split between training, testing, and the validation. So also we need to extract the features from the training and testing subset to be used with the classifier. So in our code, we have combined the different functions that were illustrated in the previous lectures, which are related to the 3D volumes, beginning from the first order features, GLCM, GLRLM, GLSZM, and finally shape features. Then we have defined a folder called MED-MNIST version 2, which is the name of the dataset or the database, that we are going to store the downloaded files, extracted features, and any other files related to the classification and evaluation process. This step is essential to organize your work. After that, we have named the dataset file, which is called nodule-3d.npz, which is an extension from the NumPy package. And then to deal with that file, you can use the load function, and this will load the content from that file into an object called data. And we have joined the path of the folder and the dataset file because we have added this file into this folder. Before going to the rest of the code, we can print the data keys, which can be accessed from data.files. When you print data.files, you will find that the different keys from that file or dataset are train images, train labels, val images for validation, val labels, test images, and test labels. So for each split, they have provided the images and the corresponding labels. After that, we have defined different configurations that can be used with the feature extraction process, such as distance and theta. And to automate the process of extracting the features from training, validation, and testing subsets provided in the data object, we have included the prefixes from the content here, because each split consisted of underscore images, underscore labels here for train, val, and test. So we have added the prefixes here and then applied a loop, and the loop here will load the corresponding images and labels and start to extract the features from them. To access that, we have accessed the data object using the key, which consisted of the initial or the prefix underscore images for images and underscore labels for the labels. Now we have the images and labels, so we need to loop on each image and start extract the features from them. And here images are volumes, so if we printed the shape of the images and corresponding labels, you will find that it consists of more than 1000 volumes. Each volume is sized 28 by 28 by 28. So to extract the features, we need to access the volume by looping on the first index of the shape, because that number will be the first index here, which is more than 1000. And then based on that volume, we can extract the features, first order, GLCM, and other features. And then we combined all of these features in a dictionary. And we have used the 2 stars here because we need to combine a dictionary to another. And finally, we have added the class, which is the labels of I, which is the index here. We have added also a try except for exception handling, because you can use a dataset or a volume that may raise error with a specific type of features. It can may raise error, for example, with the shape features or GLSM features. So to avoid any exceptions for a specific volume, we can ignore it by adding the try exception handling, and we can just print where this error occurs and what type of error, and then continue to the other volume. After completing the for loop here, we can now use the features, which is filled with dictionaries, and use pandas to convert it to a data frame, and based on that we can store this data frame into a CSV file that can be used with the classification process. We have also added a condition here to check if the file is stored, so we don't need to extract it again. So for example, if the training CSV file is exported, which contains the features for the training images and labels, and then we halted and quitted the code, and after a while we needed to repeat this process again. So if we didn't add this condition, it will start from the beginning to extract the features again from the training images. So this will check if the file exists. If so, it will continue to the other one, and this to save time. So you will need to run this code on the nodule minist. After that, you will need to run the code again on the organ minist by simply commenting this code and uncommenting this code. And you can also download any other versions of the 3D datasets supported in this database and add the path or add the name and the extension here, and this is the name and extension here, and then you need to add a prefix here. The purpose of this prefix is to avoid duplications in the naming. So when we store a file, it will be prefixed with that. It's related to this dataset or database and to the organ minist, and we are dealing with 3D. And this prefix will be added into the CSV store path here. After executing the code, you will find 3 CSV files. One is related to training, another to validation, and the third for testing, for the nodule minist, and for the organ minist. After that, you need to apply classification. We will utilize the training and testing from each dataset, training to train the classifier, and testing to evaluate the performance of that classifier after the training process. So we have utilized the same code for machine learning classification for 2D and applied it here, but on 3D. We have added calculate all metrics that we have illustrated earlier, and we have added another function for binary classification. As mentioned in the lectures, you don't have to calculate the weighted micro and macro for binary classification, because if you did that, you will find many metrics are similar in values. So imagine that we have a confusion matrix for binary classification with the values 100, 200, 10, and 20. And this is for true, and this is for predicted. This class 0, 1, 0, 1. So if you need to apply micro, macro, and weighted, you need to extract true positive, true negative, false positive, and false negative matrices or vectors from each category. So if you did that for the first class, you will find that the true positive here will be 100, and the true negative is 200, and the true positive, which is predicted to be 0, but it's not 0, which is 20, and the true negative, which is 10. And you did the same for class 1. You will find that true positive in this case will be 200, because the prediction and actual for this class is 200, and the true negative will be 100. And false positive in this case will be, it's predicted to be 1, but it's not 1, which is 10, and the false negative will be 20. So if you try to calculate sensitivity and specificity, for example, for both classes, and then calculated micro, macro, and weighted, you will find both metrics, sensitivity and specificity, for example, will be equal in values. This is because the false positive here is false negative here, and the false negative here is false positive here. And the same for true positive, it's in true negative, and true negative is in true positive. When you do this, you will find the sensitivity, for example, for class 0 will be 100, which is true positive, divided by true positive plus false negative, which is 10, and the specificity will be true negative, which is 200, divided by 200 plus false positive, which is 20. If you did that with class 1, it will be true positive, which is 200, divided by 200 plus 20, and here it will be 100 divided by 100 plus 10. This for sensitivity, this for specificity, this for class 0, and this for class 1. So if you summed and average this number and summed and average this number, you will find they will be equal, because this value is similar to here and this value is similar to here. So the specificity and sensitivity will be equal. And this is wrong. In binary classification, you need to handle a class over another. This means you need to say that I will handle the matrix for class 0 or class 1. Common choices can be to use the positive for malignancy or tumor and the negative for being normal. So if 1 is a tumor and 0 is a normal or benign, then you can utilize the matrix from here and ignore the other one. So in this function, we have calculated the true positive, false negative, and the true negative vectors, and then we can select the first or the second from all vectors to be engaged in our calculations. So here we used the first element from each vector and then calculated the different matrix and then added them to a dictionary and returned the results. If you switch it from 0 to 1, it will be similar values, but instead of handling sensitivity for class 0 and specificity for class 0, they will be switched. The sensitivity will be specificity and specificity will be sensitivity. As you saw here in our example, sensitivity is switched to be specificity and specificity is switched to be sensitivity. So now we have two functions, one for general purposes or multi-class classification and the other one for binary classification. Then we have created a function to train and evaluate the model that accepts the model and subsets for training and testing. And after that, we started to fit the model, predict using the testing subset, calculate the confusion matrix, and added a condition here to check if we have binary classification by checking the unique values in the y-test. If it consists of only two values as the length, we will call the function for binary classification, and if not, we will call the matrix for multi-class classification. After that, we return the matrix and the corresponding confusion matrix. And to execute that function, we have executed it here. But why did we use a loop here? As you notice here, we have created models list that consists of different classifiers from the scikit-learn package, which can be accessed from here by importing the different modules. And we looped on each model and then trained and evaluate that and got the matrix and the corresponding confusion matrix. And after getting the matrix, we have added the name of the model by accessing its class and its name and appended the matrix in the history. This history will be used later to be exported as a CSV file as a summary. So finally we will get CSV file that consists of which model that produced the following matrix. Also, we have created a confusion matrix display and stored it. So how to get the training and testing subsets from the files? If you scroll up, you will find that we read the two files for training and testing, then filled it with zeros for any missing values or cells. Then we have created a bar chart for the training and testing, and this bar chart will visualize the number of records per class, or in short, this is a histogram of the dataset. It can say, for example, we have 500 for training for the first class and 200 for the second class. This is for training and this is for testing. Then we extracting the training and encoded it, and extracting the testing and also encoded it using the label encoder and used them with the model. As you notice, we have train path, test path, and we have fig store path and results store path. We have defined them at the top of the code. Here we did a version for the nodule MNIST features and the same for organ MNIST features. If you need to execute the organ MNIST features, you can comment this and uncomment this. When the code is executed for the nodule, it will display this bar plot for training and for testing. And as you see, the dataset is imbalanced. Imbalanced means the number of records per class is not equal, with a significant gap. As you see, there is more than 800 for class 0 and around 250 for the second class. So there is a large gap here and here. For the metrics, in Excel, we have created a mean column, and these values is the average of all of the previous metrics, and this can be called mean metric, which can judge the performance or the overall performance by summing each record and dividing it by 5. So the top one will be at a post classifier that reported more than 75%. And as you see here, the specificity is low for all of the classifiers. The reason behind that is the imbalanced dataset. As you remember, we have selected that true positive, false positive, true negative, and false negative can be extracted from the first class, so the specificity will be calculated from the second class, which is true negative divided by true negative plus false positive. And if you change it in the function from 0 to 1, you will find that the specificity here is high, but the recall or the sensitivity is low. Using this or that, we got a performance of about 75 for this dataset. And this is the corresponding confusion matrix for the data post, and the second top one, which is gradient posting, that reported about 73. When we apply this for the organ MNIST, which consists of 11 organs, it displays a bar plot for training and testing, and also, as you notice, the dataset here is imbalanced. And this is the corresponding performance where the gradient posting classifier reported the highest performance, about 70%, as a mean metric, and we have only included the weighted metrics here because the data is imbalanced and we are dealing with multi-class classification. Again, this column is created in the Excel file by summing all of these values and dividing it by 5. As you notice, there is empty cells here because this can happen when a division by 0 occurs during calculating the metrics. So it will report a null value that will be reflected by an empty cell in the Excel file. A solution for this, you can add a small value called epsilon to the denominator for each metric to avoid any divisions by 0. And this is the confusion matrix for the gradient posting and extra trees, which is considered the second top, and here extra trees reported 70%, 0.30. And as you see in fusion matrix on the left, there is an issue with number 9. As you see, there are many values in the true positive and the true negative cells for 158 and here 6247 and so on. So if we simply omitted that organ from the dataset, the performance can be increased because other organs, as you see, there is no misclassification cells as defined as false positive and false negative. For example, 8, there are many zeros here, 7, there are many zeros here, and so on. And our target is to increase the true positive and true negative, which can be summarized in this diagonal. So in this lecture, we have dealt with 3D datasets by acquiring it from the MNIST version 2 database and dealt with two datasets, one for binary classification and one for multi-class classification. Then we revisited again the code for machine learning classification, but instead of dealing only with a single classifier, we have created a list of multiple classifiers and we have compared between them to report the best classifier that fit on the current data. We have also declared a new function for binary classification to calculate the corresponding performance metrics. Instead of dealing with multi-class classification performance metrics, micro, macro, and weighted, we can simply calculate it from the initial index or the second index. And we have discussed the reason behind that. Finally, we plotted the confusion matrix and bar plot, and from the bar plot in the training and testing, we can judge if the dataset is balanced or imbalanced.